Hi students, today we are going to define terminal velocity and also derive an expression for the terminal velocity. Now let us consider a small metallic sphere is dropped freely inside a highly viscous liquid. You can see in this picture. So this is the metal sphere and this beaker is containing a liquid of high viscosity. So for example, I can take this as a glycerin, okay, glycerin oil or castor oil which is having high viscosity. Now what will happen when a sphere is dropped in the air? First of all, in air if you drop a sphere means it will start from zero velocity. So the initial velocity of the falling body will be 0. Then as it is descending down in air, what will happen? The same thing should happen here also, is it not? Because in both the cases, the sphere is falling freely. For a freely falling body, the initial velocity is equal to 0. But as it is descending down, at each and every step, what will happen to the velocity of the sphere? It will increase continuously. That is, because of the increase in velocity, the metallic sphere will be accelerated. Is it not? Whenever it is accelerated in the downward direction, it crosses through the different layers of the liquid and it is being opposed by a force which is called as viscous force. So whenever the sphere is descending in the downward direction, first force acting on it is its own weight, that is W. This weight is the gravitational force acting on the sphere and this acts in the downward direction. Also when the sphere is passing through the liquid, it displaces equal volume of the liquid. It displaces equal volume of the liquid. As a result, it experiences another force in the upward direction that is called as upthrust. So here U is the upthrust. Now, in addition to the weight of the body and the upthrust, another force also is acting on the same sphere. That is called as viscous force or viscous drag. Okay. So that force is denoted by capital F. Now, the moment you drop the sphere on the free surface of the liquid, that is at the initial velocity U equal to 0, there is no viscous force. But the moment it crosses each and every layer of the liquid inside the vessel, the velocity of the sphere increases and proportional to that the viscous force also will be increasing. So at each and every stage the velocity will be continuously increasing and the viscous force also will be increasing. But after traveling through some depth or distance inside the liquid, the final velocity, which is also called as the terminal velocity, attains a constant value beyond which there is no further increase in the velocity of the descending sphere. Okay? At that velocity called the terminal velocity, the net downward force acting on the sphere, the net downward force means W minus U. That is the net downward force acting on the sphere, that will be equal to the viscous force. Such a stage is attained. At that stage, the velocity is called as what? A terminal velocity. After that, the velocity will remain constant. So till the body attains a terminal velocity, from 0 to maximum, the velocity will increase. After attaining the terminal velocity, there is no further increase in the velocity. Understand? So at that terminal velocity, the net downward force acting on the sphere is equal to the net upward force, that is the viscous force. So when the net force acting on the sphere, upward force is equal to the downward force, means the net force acting on the sphere will be equal to 0. Since the resultant force acting on the metallic sphere is equal to 0, there is no acceleration. Is it not? Therefore, it will fall. Further, it will fall with a constant velocity. That constant velocity only is called as the terminal velocity. And this is denoted by the symbol V suffix T. Okay. Now, In this picture, I have shown a metallic sphere, and let R be the radius of the sphere. Then, since it is a metal, it will have a greater density than the liquid. So, let rho be the density of the metal. Okay, density of the metal with which the sphere is made up of. Then sigma is the density of the liquid. So, liquid is having a density sigma. Rho is the density of the metal. Then eta is the coefficient of viscosity of the liquid. So, what is the coefficient of viscosity of the liquid is eta. Next, W is the downward force called the weight acting on the sphere. That is weight of the sphere, which is nothing but what? The gravitational force. So, this also can be represented by Fg, gravitational force. Then U is the upthrust on the sphere. The upthrust acting on the sphere exerted by the liquid in the upward direction. And F is the viscous force. The viscous force in this example, it is acting in the upward direction because the sphere is descending in the downward direction. This viscous force is an opposing force. If the direction of motion is downward, means viscous force will be upward. If the direction of motion is upward, means viscous force will be downward. Is it not? So, in this picture, since the direction of motion of the sphere is downward, the viscous force is acting in the upward direction. Okay. Now, the three forces acting on the sphere are weight in the downward direction, upthrust U in the upward direction, and viscous force capital F also in the upward direction. Okay. So, I will take the net force. So, W is acting in the downward direction. This should be equal to U plus F, or W minus U must be equal to F. This W is also the gravitational force. So, Fg minus upthrust is equal to the viscous force F. So, in this equation 1, now we are going to substitute the expressions for Fg, U and F. So, the weight Fg is also equal to the weight of the sphere. So, it should be m into g. So, this is also equal to volume. Mass is volume into density into g. Now, the shape of this metal is spherical. So, volume of a sphere formula, if I substitute, means it is 4 by 3 pi r cube into rho into g, and this is expression number 2. Therefore, Fg is now equal to what? 4 by 3 pi r cube into density rho into g. Okay, now what is the expression for the upthrust? Now, when the sphere is descending inside the liquid, it displaces equal volume of the liquid, is it not? Therefore, upthrust must be equal to the same volume, that is 4 by 3 pi r cube. Instead of rho, here we have to substitute the density of the liquid, that is sigma into g. So, this is equation 3. Okay. And the viscous force capital F is equal to 6 pi into coefficient of viscosity eta into r into v terminal velocity. So, this is equation 4. When the sphere's velocity is continuously increasing at one stage it will attain a maximum velocity called a terminal velocity, at which the net downward force is equal to the viscous force. So, this Fg minus U is called as what? Net downward force, and F is called the viscous force. In this equation, I am going to substitute 2, 3 and 4. Okay. So, I will write once again net downward force is equal to the upward force, namely the viscous force. So, I am going to substitute in equation 1. So, instead of Fg, what I can substitute now? 4 by 3 pi r cube. So, 4 by 3 pi r cube into rho into G minus upthrust is what? 4 by 3 pi r cube sigma into G. So minus 4 by 3 pi r cube sigma into G is equal to this viscous force. This equation is derived, okay, this is the derivation, okay, done by Stokes, and also it is a derivative from Stokes law, okay. Stokes law gives this equation. So I am going to substitute here 6 pi eta r into terminal velocity. Understand? Now some common terms are there on the left hand side, we can take them out. So we will write 4 by 3 pi r cube into rho minus sigma into G is equal to 6 pi eta into r into Vt. So this pi can be cancelled on both sides. Pi term gets cancelled. Then this radius of the sphere r gets cancelled with the power 3. So r cube becomes r square. Now this 4 by 3 number is there, here 6 is there, is it not there? So I can divide this 4 by 2 and 6 also by 2. Otherwise this 3 into 6 becomes 6 3s are 18, 18 divided by 4. Like that also I can write that. So r square into rho minus sigma into G. This is equal to 6 into 3 is 18. By this 4 will come down, 18 by 4 into eta into Vt. Now what is the title? Expression for the terminal velocity Vt, is it not there? I want an expression for the terminal velocity. So I take terminal velocity Vt on the left hand side and remaining factors can be adjusted now. So that this will become what? 9 by 2. So 9 by 2 eta into Vt is equal to r square into rho minus sigma into G. Or terminal velocity Vt is equal to this 9 by 2 goes to the right side by what? 2 by 9 into r square into rho minus sigma into G whole divided by the coefficient of viscosity. So this is equation number 5. This is the required expression. We have derived the required expression for the terminal velocity. This is the constant velocity attained by a descending metallic sphere in a liquid at which the net downward force acting on the sphere is equal to the viscous force. Okay. So from this equation you see 2 by 9 is a constant. It is a constant. Rho is the density of the metal and sigma is the density of the sphere. G is acceleration due to gravity and eta is a coefficient of viscosity. All these are constants. Therefore, we can write R V terminal is proportional to R square. So this is the relationship connecting the terminal velocity and the radius of the sphere. Now in this equation, okay, in this expression, I have considered glycerin, which is a liquid, and the sphere is made up of a solid, so that in this picture rho is greater than sigma. Suppose what will happen if rho, the density of the solid, is okay here greater than sigma. Suppose you imagine any other sphere like air bubble is moving through a liquid, so that the liquid's density is sigma and the density of air is rho. So in this case what will happen? For rho of air is less than rho for a liquid, and hence the terminal velocity will be negative. Is it not? In this equation terminal velocity will be having a positive value because the density of the metal is greater than the density of the liquid. Suppose if you imagine a spherical air bubble is moving inside a liquid. Air bubble is made up of air and density of air is less than the density of the liquid. So it cannot descend in the downward direction. Because of terminal velocity it will move in the upward direction. Is it not that? So that is why terminal velocity is coming in negative. So for example, air bubble will always ascend, okay, it ascends upwards, okay, it ascends upwards inside water. We have seen many times when you put a vessel inside the bucket of water, air bubbles will always rise in the upward direction. So air bubbles are spherical in shape, and air is having a density which is less than that of water, and hence it is rising in the upward direction. Okay. So the expression for terminal velocity is what? Vt is equal to 2 by 9 r square into rho minus sigma g divided by eta. Now, when you come for the practical class, in the practical class, the terminal velocity can be measured by using a stop clock. Okay. So the distance traveled by the sphere from initial position to the final position can be measured, and also if you divide it by the time which is measured by a stop clock, Vt can be directly determined, from which you will take eta to the left hand side and Vt to the right hand side. So the coefficient of viscosity of the given liquid can be measured. So this will be your practicals experiment. I hope you must have understood well. Fine.